Thank you very much for the invitation. The talk will not contain my own results. It will be just an attempt to explain to you and to myself a paper of Donoho and Tanner. So I will be, we shall consider the following problem. We have a signal which we call x0, and it has n coordinates, xn0, and we know that it is positive or non-negative, more precisely. So all coordinates are non-negative for all I. And we don't know this signal. Instead, we know some transformation of the signal. We call it y0, and it is some matrix A applied to x0. Here, A is a linear transformation, Rn from Rn to Rd, and n is maybe much larger than d. So the transformation lowers the dimension. It is a linear transformation. And now our problem is to reconstruct the signal x0, reconstruct x0 from the image y0, which has lower dimension, and the matrix A is also known. And now one natural method to do this is as follows. One takes any function of x and tries to minimize it subject to the following conditions. Subject to the condition that x is a preimage of y0. So we take all preimages of y0, call them x, and impose this condition. Also, we impose the condition that all the coordinates are non-negative of this preimage. And then we try to minimize some function of this preimage. And for the following, it will be not important which function we take, because we shall be interested mainly in the problem when when these two conditions determine x uniquely. So the problem which will be interested in this connection is whether these two conditions determine x uniquely. And if this is true, then of course the solution must be x0. So then the reconstruction is possible. And now this problem has been studied among other problems in a paper of Donoho and Tanner from 2010. And the basic assumption we shall need, or they need, is the following. So the result will depend not on x0, but rather on the number of non-zero coordinates of x0. So let us assume that x0 has exactly k non-zero coordinates. So the number of I such that xi0 is not 0, which means it is strictly positive, is k. Now this means that x belongs to a face of the positive orthant. So we have here, this is called the positive orthant, and it is a convex cone. This condition means that x0 belongs to a relative interior of the face of this orthant, which has dimension k. So more precisely, let us define the following face of Rn plus. So in general, the faces of Rn plus are determined by saying that, well, Rn plus consists of all vectors with non-negative coordinates. If we want to have a face of Rn plus, we have just to say some of the coordinates are 0 and the others are 3 non-negative. This determines a face. So faces correspond to subsets of the set one of the set of n coordinates. And we consider the face which consists of all elements which are 0 at the same places at which x0 is 0. So it is called F, and it consists of all y in Rn plus, such that yi is 0 for all I not equal to I1, Ik, and I1, Ik are exactly the places where this x0 has non-zero coordinates. So at places I1, Ik, x0 has positive elements. And we consider now the face where these coordinates are free and the others are 0. Of course, x0 belongs to this face. And now the main observation of Donahoe and Turner is the following. They observed that the following two conditions are equivalent. The first condition is called survive in their notation. A, F, R, n plus, and it states that the image of F, so F is a face of the orthant, and we can map this face by the map A, and then this condition says that AF is also a k-dimensional face of the image of ARRN plus. So we have the following picture. We have the positive orthant Rn plus. We map it by a matrix A to the d-dimensional space where it is the image is some cone. And now here we have a face in which x0 is located. And the first condition says that the image of this F is again a face of the image of the orthant. Because in general, it could be that this face is mapped to some interior of the orthant or something like this, so that it is not a face anymore. So the first condition says it is again a face. And the second condition, which is equivalent to that, so the claim is they are equivalent, is that the system, the linear system, so this condition is called unique. The system AF, the system AX equals to Y0 has a unique solution in the orthant. So the variables x which satisfy this condition are possible candidates for a recovery. We know that x0 satisfies this condition. Now we want to recover x0, which means the possible candidates are exactly the vectors which satisfy this condition. And of course, everything is restricted to this orthant. And now if the solution in this orthant is unique, then this condition is satisfied. So the claim says that these two are equivalent, and the only thing we need to know about the matrix is the following assumption. So they are equivalent under the following assumption. that the matrix A is in general position, which means that the columns of A are vectors in general position. Of A are vectors in general position. More concretely, this means that the columns which are vectors in the d-dimensional space satisfy the following condition: if we take any d of them, then they are linearly independent. And now this is a very actually an observation which is not very difficult, but it's very useful because it allows to translate a problem into a different language. So now our problem was whether this solution is unique, and now this idea allows to translate it to a problem of counting faces of the projected orthant in this case. Let us make a remark. So the second condition, the uniqueness, is also equivalent to the following condition. We take the pre-image of the vector y0, which is an affine subspace of Rn. It's an affine subspace of Rn, and we want to intersect it with the positive orthant, and we want that it is just one point, x0. This is what the uniqueness condition states. Or this can be stated as follows. This pre-image can be written as the kernel of A shifted by x0. And we want that this shifted kernel intersects Rn plus only at x0. Or another equivalent restatement is the following one. So we take x0 and we start with x0 in some sense, and we want to add to it something and stay in the Rn plus. And that's why we can write it as follows: the kernel of A intersected with the tangent cone at f of Rn plus, I denote it in this way, and I will define it in a moment, is nothing, is trivial. Here, the tangent cone Tf of Rn plus is the following cone. It's a convex cone. It consists of all directions y. Maybe y is a bad notation because, no, it's not a bad notation because we call that y, but let me call it z. Such that, so it's the set of all directions such that if we start at x0 and look in direction z, then we look inside the cone, Rn plus in this case, for some epsilon greater than 0. So imagine we are in x0, and now we look in all possible directions. Those directions which show inside the cone are called, or they are elements of the tangent cone. So this tangent cone is a convex cone in the n-dimensional space, and in our case, it is something very simple. If we start at x0, then x0 has k coordinates which are non-zero, and we can add to these coordinates everything, any small number, and stay positive. So in these coordinates, we can add everything, and at coordinates which are 0, we can add just non-negative numbers in order to stay here inside, which means that this cone is isometric to the cone of the following form. In k directions, we can add everything, and in n minus k directions, we can add only positive numbers. So it's a direct sum of two cones. And now our question is the following one. we have a matrix A, and this matrix has a kernel. The question is whether this kernel intersects this cone or not, or more precisely, whether it intersects it non-trivially. And this is a very special setting of what can be studied using conic intrinsic volumes. So let me define the conic intrinsic volumes. First of all, we need to define what a polyhedral cone is. A polyhedral cone C is an intersection of finitely many closed half spaces. So let us call them xi plus, I from 1 to n, or 2, maybe not to n, to capital N, and h1 plus and so on, hn plus are closed half spaces whose boundaries pass through the origin in Rn. So we take half spaces, intersect them, and what we get is a cone, a polyhedral cone, more precisely. Now, given a polyhedral cone, so it's a, in other words, it's a set of solutions to define a system of linear inequalities or linear homogeneous inequalities. And now, given such a cone, we can define its conic intrinsic volumes. So conic intrinsic volume is a notion which is similar to the notion of intrinsic volumes, but intrinsic volumes are defined for convex bodies, whereas conic intrinsic volumes are defined for convex cones. So let's C be such a polyhedral cone, then its conic intrinsic volumes of C are defined as follows. For K, so they are indexed by K from 1 to n. N is the dimension of the space in which we are living, and the kth conic intrinsic volume of C is the probability that a projection on C of a uniformly distributed random vector on a sphere belongs to the relative interior of some face for some face f of dimension k of C. So more concretely, this means the following. First of all, we need to define some notions to make it to make everything clear. So first of all, P pi sub C is the metric projection onto the cone C. It is a map which assigns to a vector Z the minimizer of the following function, Z minus X. This is just the Euclidean norm over all X in C. So we take a convex cone C and we try to find a vector. So here is a vector Z, and then we try to find a vector X in C which minimizes the distance to Z. In this case, it looks like here. So if Z would be that would be the metric projection. If Z would be here, then the metric projection would be Z itself. If Z is here, we have this. And finally, one can understand how it looks. So if this is the so-called dual cone, then the projection is 0. So all these Z are projected to 0. Yeah.
Zakhar, just one question, maybe from the beginning. Yeah. At the beginning, when you really the first page,
Yeah.
When you actually define your method to you have a function to minimize, or you just actually have some condition under which actually a linear system of equation AX equal y0 as a unit. Maybe it was really at the beginning.
Yes. So, by the way, it's not
really
my
the
method.
top.
It's the method of Donohoe-Tanner.
Yeah. So in the method in which actually what is the rule of the function j? Because I think that you just give condition under which the linear system ax equal y0 just have
He
one
doesn't play any
solution
role.
in the. Okay.
He doesn't play any role.
So it's not the L1
in his
norm. It's not
considerations.
something like.
Sorry.
Okay. It's not the L1 norm. It's some. Okay.
It could be L1 norm, but we are just investigating, at least now, the question whether the solution is unique. If it is not unique, of course, it is important how to choose this function. But if it is unique, it's not a.
Yeah. Okay. You just have to pick the solution.
But
okay.
Of course, one can ask what happens if this is L1 norm, and then something similar can be applied too. But then we shall have here the descent cone of this norm. So we shall, our condition will be of a very similar type. It will be the condition that the kernel of A does not intersect or intersects trivially this tangent space modified by the descent norm, something like that, by the descent cone of the L1 norm, intersected with that cone, right? So it will be a slightly different cone.
Okay.
Or what was it there?
Yeah. For me, it's okay.
Yes.
So may I ask a question?
Yes.
So I guess the way I understood Donohoe result is that we are trying to solve a system not in the positive quadrant, but in the whole. We are trying to solve a system for x's belonging to R, and then I think the L1 norm is necessary. Isn't it the case?
I don't know. I'm not sure. What is the?
Okay, because
maybe it's a different result of the Donohoe-Tanner.
Okay, maybe because you are now trying to solve a system for the positive quadrant, so for all x's which are positive. Okay,
right.
And I think I think in case when you are trying to solve the system, in case when x is in you don't impose the positivity constraint, but you simply have no unique solution then.
Right, of course, this complete kernel will be a solution.
Yeah, and I think this is the reason for which we have to use L1 norm then to decide.
Yes, and if we do it, it reduces to a problem of a very similar type. The recovery will be correct by this method, by this minimizing L1 norm will be correct, if and only if the kernel of A intersects the decent, so some different convex cone trivially. So the type of the problem will be very similar. Just this cone will be different.
Okay, thank you. Yeah. I think this is good. I think me and Patrick were trying somehow to relate it to the result which we often use in the statistics. Thank you.
Okay. And so all these problems are of the following type. We have a linear subspace, maybe a random. So we can, at some point, we can assume the matrix A is a Gaussian. Then this is a random uniform subspace, linear subspace, and we want to know what is the probability that it does not intersect some cone. And in this case, it is this very simple cone. In general, it may be something more interesting. Now, the problem can be solved by some tool from integral geometry, which is called the Conic-Crofton formula. And to state this formula, we need the notion of conic intrinsic volumes. So if we have a cone C, then the kth conic intrinsic volume is defined as follows. We define the metric projection into this cone, which is defined in this way as a minimizer. And then the projection belongs to the cone, of course. And it is known that the cone, it is a basic fact that the cone C is a disjoint union of the relative interiors of its faces, overall faces of C. A relative interior of the face is the set of all points which belong to the face, but not to a face of a small dimension. So if you say, if you have something like that, if that is a face, then the relative interior will be everything except the boundary. of the face. So it's essentially the interior, but it should be taken with respect to the ambient linear hull of the face. And now if C is a disjoint interior of is a disjoint union of such relative interiors, this means that X will be that the metric projection will be contained in a relative interior of a uniquely defined face. So for example, if Z is this point, then it is contained in a unique in the relative interior of this half line. And this face has some dimension. And now if this dimension is K, then we say that this contributes to the Kth intrinsic volume. And finally, here in this definition, U is a uniformly distributed random vector on the d-1 dimensional sphere. So we take essentially a random direction and we look to a face of which dimension it projects. And the probability that it projects to a face of dimension K is the Kth conic intrinsic volume. Now, just to mention one simple example, if the cone is n-dimensional, so if its dimension is full, then the nth conic intrinsic volume is the probability that a point is mapped to the, or that a point is a random direction is projected to the cone itself, which means to the interior of the cone, which means it should be in the cone. It should be contained in the cone, so it is just the probability that a uniform direction is contained in the cone, and this is just the angle, the solid angle of C. So conic intrinsic volumes are something which are more general than the solid angle. Now, some properties of the conic intrinsic volumes. First of all, it follows directly from the definition that the sum of the conic intrinsic volumes is 1, because it is a sum of probabilities, and any point is projected to some face of some dimension, which means if we sum them over K, we get 1. And this means, and also, of course, they are non-negative, which means they form a probability distribution. 0, 1 of C, 0, n of C form a probability distribution. And let us denote by xc a random variable with this distribution. So this random variable takes values from 0 to n, and the probabilities are just these intrinsic volumes, xc. So sometimes it's convenient to think of it as a probability distribution and to consider a corresponding random variable. Now, this was the first property. The second property is that the alternating sum of these volumes is 0, which is somewhat unexpected because, by the way, the first property is expected, but it has no analogon in the usual convex geometry. So if we just consider the usual intrinsic volumes of convex bodies, they do not have any property of this type, and they also do not have any property of that type. So the sum is 0, but there is one exception. The exception is the R linear spaces. So if C is not a linear space, then this holds. And for a linear space, the conic intrinsic volumes are all 0 except one of them, which is 1. So they form a trivial probability distribution with a single atom at the dimension of this space, and this is 0. If this is not 0, then. And now let me state the Conic-Crofton formula, which is the basic tool to compute probabilities that a random to compute the probability that a random linear subspace intersects a cone. So the Conic-Crofton formula says the following: if we take a cone and if we try to intersect it with a random linear subspace of codimension L. So this is random uniform linear subspace of codimension L. And so we take such a subspace, intersect it with C, and we want it to be non-zero. Then this probability can be expressed through the conic intrinsic volumes. It is the L plus first intrinsic volume plus the L plus third intrinsic volume plus and so on, and the sum is overall odd indices here, L plus some odd number. But for the following and for asymptotic considerations, it's very convenient to think of it as some slightly, it's not exactly equal, but it is approximately the same as the probability that xc, this random variable, is larger or equal to L. Why? Because to be larger or equal to L, it has either to be odd, either to be L plus some odd number, or it has to be L plus some even number. But these probabilities, odd and even, are asymptotically, in many asymptotic situations, the same. So just think of it as such a tail probability. And now maybe we can return to the example studied at the very beginning. We need to now assume that A, the matrix,
just one thing about your approximation. I guess that it works when actually n and you have just n in this case. N is very large, right?
Right.
It's asymptotic, right? Because what you say, it's the probability, the conic intrinsic volume of L plus 1 is approximately, in this case, equal to the conic intrinsic volume of L plus 2 and so on, right?
I say exactly. I say that they do not change very much. I say, for example, L plus 1 is almost the same as L. L plus 3 is almost the same as L plus 2, something like that.
Yeah, okay.
But I don't claim it's
clear.
a rigorous result, just to think of it.
Okay.
And now let us consider the following example, again, following the Noether and Tanner. So, example, the cone we are interested in is just the positive orthant times the whole Euclidean space. Now let us take just the positive orthant. And let us compute, say, in dimension n. And let us compute its nth intrinsic volume. Okay, so here is the orthant. And now suppose we have some vector x or some vector z in Rn. It is z1, z2. Let me just take some example. Z is 0, 1, -1, 2, -2, 3, 3. What is the projection of this vector to Rn plus to the positive orthant? Well, it's clear that all positive coordinates can stay as they are, and all negative coordinates have to be replaced by 0. So the projection is 0, 1, 0, 2, 0, 3, 3. And now this projection belongs to, in this case, it belongs to a face or to a relative interior of a face with dimension. Well, the dimension of the face is the number of non-zero coordinates, 1, so it's 4 here, right? Because this face consists of all vectors in which zeros are placed at these 2 points, at these 3 places, and all the other coordinates are free, non-negative. And the number of other coordinates is 4, so the dimension is 4. So if we use this projection, then we project a vector to a k-dimensional face if and only if the number of positive coordinates is k, right, in the vector. And so we have to compute the probability here, the probability that the number of positive coordinates, by the way, I forgot here plus, we have to compute here the probability that the number of positive coordinates of a random vector u is uniform, is L. But instead of a uniform random vector, I can take a Gaussian random vector, because both of them are rotationally invariant, isotropic, and the probability doesn't change. So let us take u to be Gaussian, and then the components of u are independent, and we want to compute the probability that L components are positive. Now each component is positive with probability 1/2, so it's just a binomial distribution with parameter 1/2. So what we get here is 1 over 2 to the power n over L. And this means that the corresponding random variable is binomial, exactly, with parameters n and 1/2. So these are the conic intrinsic volumes of the orthant in dimension n. And now the asymptotic properties of this random variable, for example, the central limit theorem, the most important thing, determine the phase transition in the problem we started with, namely the probability that the solution in the orthant is unique. So it is the probability that the solution to the system AX is equal to Y0 in the non-negative orthant is unique. It is the probability that the kernel, let me write it again, it is the probability that the kernel of A intersects the cone Rk times Rn minus k plus trivially. Now, assume A is Gaussian. Then this kernel of A, so it's a matrix, a Gaussian random matrix with Gaussian entries. Then this kernel is a subspace of codimension D. So the codimension here is D with probability 1, and it is uniform on the set of all such subspaces. So it is uniform on the Grassmannian of n minus t dimensional linear subspaces. And we are exactly in the setting of the Crofton formula, but we have here equal to 0. In the Crofton formula, we had non-equal to 0. So let us consider the complementary probability. It is 1 minus p. The same thing is not equal to 0. And now we can write it using the random variable. But we need actually a random variable corresponding to this cone rather than to this one. So let us look at the cone x. And the cone x are k times, so it's a direct product. I'm sorry, it's a direct product. Well, maybe it's the same. R n minus k plus. What is the random variable? What is the distribution of this random variable? Okay, so this multiplication with rk plus just shifts all dimension by k, which means that the corresponding random variable will be just a sum of k plus a binomial random variable with parameters n minus k 1/2. Right, so by this I just mean that we take a random variable with this distribution and shift it by k at k. So it is this random variable, and now by the Crofton formula, let me write this approximative result. By the conic Crofton formula, this is approximately the same as the probability that this binomial random variable plus k, so k plus binomial n minus k 1/2, is smaller than d, smaller than the codimension. Or, and of course, okay, we have here approximately, but if you want it to be exactly, you have to take this sum over odd or over even numbers. And now this is the same as the probability that a binomial random variable with parameters n minus k 1/2 is smaller than d minus k. And now let us assume that we are in the asymptotic setting where n, k, d maybe all go to infinity with some speeds. Then we can look at the binomial distribution with parameters n minus k and 1/2. And let n minus k also go to infinity. Then its mean is n minus k half, and it is concentrated around this mean. So it's there is a central limit theorem saying that it is concentrated around this mean. So here is the mean. And now this probability, or the behavior of this probability, depends on whether the number d minus k is smaller or larger than the mean. So if, for example, we are here, if d minus k is smaller than the mean, then the probability is going to be 0, or it converges to 0. It's exponentially small. So here, in this setting, p unique is 0, or it's almost 0. In the other setting, when d minus k is greater than 1/2, it is almost 1. So the phase transition, which we observe here, depends on the mean of the random variable x associated to the cone under consideration, essentially. And this mean is called the statistical dimension, and it has been introduced in a paper of Amelungsen, Lotz, McCoy, and Trop, which is in the abstract, is mentioned in the abstract, and it plays an essential role in these phase transitions because it is exactly the place where the phase transition occurs in a general setting, not just in this example. Now, we proved essentially, so it can be made reverse everything. We proved that there is a phase transition for the probability at the following point. So the phase transition occurs if n minus k half is approximately equal to d minus k. I don't want to be very, very precise here, just a rough idea. And if we solve it, we see k smaller than 2d minus n is the condition under which we have uniqueness. So if we have this, then okay, so the phase transition is if they are equal, but if we have this, then p unique is approximately 1 in some asymptotic setting. So we can assume they are all linear functions of n, say k and d are linear functions, grow linearly in n, and then we can write it as an inequality under which this holds. Now, of course, what we considered was just a very simple example with a cone for which one can compute the volumes, the intrinsic volumes exactly. The number of cones for which we can do this exact computation is very restricted, but there are general results which say that in some sense we have a central limit theorem for the volumes of the intrinsic volumes of the convex cone under very general conditions, which means that under very general conditions, a phase transition of the same type should occur. So I don't know much about optimization, but it seems that one can imagine many problems for which reduce to the same type of question, so to the question whether a random linear subspace intersects a cone. And in all these questions, there is universality because there are general results which state this. For example, here is just one of them, general results on the random variable xc, and one of them is the following. Let us denote by delta c the statistical dimension of the cone, which is the sum of k nu k of c, k from 1 to n, and it is nothing but the expectation of the random variable associated with the cone. This is called statistical dimension. And for example, for the orphaned, it is n½ because it is this expectation. And now the following result is a central limit theorem. Sorry. Is a central limit theorem for conic intrinsic volumes due to Goldstein and T. It says the following: consider a sequence of cones Cn. Cn is a cone in a subspace in a space of dimension Dn, and assume that the statistical dimensions go to infinity of these cones, and let us also denote by tau squared of Cn the variance of x Cn. So the variance of this random variable. Then xCn satisfies a central limit theorem. We normalize by the expectation divided by the square root of the variance, and as n to infinity, this converges to the standard normal distribution in distribution, provided some minor condition holds. Provided that the limit of the variance divided by the dimension is non-zero, is positive. So under very general conditions, such a result holds, which means we expect the same shape of the phase transition under very general conditions. And the point at which the phase transition occurs is the statistical dimension. Another result due to Amelunxen, Lotz, McCoy, and Trop is a concentration inequality. So concentration inequality for this random variable around the mean is also available. Now maybe it's time to stop at this point.